All right, welcome to another exciting installment of sampling distributions. Yesterday, we talked about sampling distributions with proportions, and today we're going to talk about sampling distributions with sample means. What does the Roman Colosseum have to do with sample means? Probably not much, but it's a pretty cool picture. Learning targets. Today, you're going to tell yourself, I can find the mean and standard deviation of the sampling distribution of a sample mean x bar. That's like your x with a little bar above it. I can explain how the shape of the sampling distribution of x bar is affected by the shape of the population distribution and the sample size. And I can use a normal distribution to calculate probabilities involving x bar. Again, it sounds like a lot of targets, but a lot of these can be really done with a single sentence. So really, we're going to learn all about sampling means. All right, the mean of a sampling distribution. The mean of the sampling distribution is equal to the mean of the population. So x bar equals mu x bar, which is equal to the population, the mean. So again, if, men lived on average for 72 years, um, I would and I randomly took a sample of 100 men, uh, 2,000 different times. The average of all those 100 samples of men would be around 72. And the standard deviation, the sampling distribution of x bar is, it's just going to be sigma of x bar is equal to standard deviation over the square root of n, where n is your sample size. Pretty straightforward, pretty fun, pretty exciting. Yes. Go Wildcats. The behavior of x bar in repeated sample is much like that of the sample proportion of p hat. So a lot of the things that we saw yesterday with the sample proportion, we're gonna, like Mr. Joe, like this sounds like deja vu. If you don't know what deja vu is, go ask Miss Taylor. But anyways, like the sample proportion, the sample mean of a sample is an unbiased estimator. So that means again the sample mean is the population mean because it is an unbiased estimator. Um, the values of x bar again are less spread out for larger samples. So the more information we get in, the more data that we receive, the less sort of variability of all information. Um, and because it's standard deviation divided by square root of n, the sample size needs to be 4 times bigger to cut the standard deviation in half. Um, and again, we can only really use this if that 10% condition is met. Remember yesterday, we said that the sample size has to be less than 10% of the population. Again, same rules apply. Again, it sounds like a lot of deja vu, but it's not. And if the population distribution is normal, then dun dun dun, the sampling distribution of x bar is also normal. Crazy. What? Mind blown. Again, this is also true no matter the size of the sample. That was a lot of information, real fast. But that's really all you really need to know. And so, why don't you rest your little brain with this fun, relaxing picture of Italy? Take a deep breath, put on some calm, soothing music, maybe a little beach waves. That doesn't make sense. But, anyways, let's move on to our first example. Example 1. The height of young women follows a normal distribution with mean 64.5 inches and a standard deviation of 2.5 inches. Find the probability that a randomly selected young woman is taller than 66.5 inches and show your work. And B, find the probability that the mean height of a simple random sample of 10 young women exceeds 66.5 inches. Again, show. So, step 1, state the distribution in values of interest. So we have let x be the height of the randomly selected young woman. The random variable x follows a normal distribution with mean of 64.5 and a standard deviation of 2.5 inches. We want to find the probability that x is greater than 66.5. Again, this is sort of how you would answer a AP question. Like they want you to say all the given information in basically stat language. And this is how you would sort of state that information. Step 2, perform the calculations and show your work. So you can just simply just plug this into your calculator. The lower bound is 66.5 with a really, really big upper bound because we're looking at all the possible values of all the possible sort of samples that could have 66.5, greater than 66.5 inches of height. And so we're looking at the possibility of getting a height greater than 66.5. So we're going to look at all the possible sample means of the sample distribution greater than 66.5. Plug it in with a mean of 64.5 and standard deviation 2.5. And we get a probability of 0.1, not 1, I don't know why I said 1, 0.211855. And so around 20-ish%. And so answer the question. The probability of choosing a young woman at random whose height exceeds 66.5 inches is about 0.21. Crazy. And really all the information you need to show is just this sort of chart right here with a curve and that shaded in area along with those numbers at the bottom of the x-axis. That's really all the information you need to share to get credit for it. Crazy, I know. So then part B, step 1 of B, see the distribution in the values of interest. Again, remember, we are looking for, instead of looking at the entire population, we're looking at a simple random sample of 10 women. So for an SRS of 10 young women, the sampling distribution of their sample mean height x bar will have the mean 64.5. The 10% condition is met because, well, certainly there are more than 100 young women in the population. 10 times 10 is 100, and there are at least 100 young women in the population. And the standard deviation is going to be equal to 2.5 divided by the square root of 10, which is equal to. And so remember, step 1 of B is looking for same information, but instead of looking at the whole population, we're looking at a simple random sample of 10 young women. And so for an SRS of 10 young women, the sampling distribution of their mean height x bar will have the mean of 64.5. The 10% condition is met. 10 times 10 is equal to 100, and there are certainly more than 100 young women in the population. The standard deviation is equal to 2.5 divided by the square root of 10, and that is equal to 0.79. And so, because the conditions are met, the sampling distribution is normal because the population distribution is normal. Remember from earlier in the slides. We want to find P of x bar being greater than 66.5 inches. Notice this is x bar because x bar again is the mean of the sample as opposed to x. Again, perform the calculations. You would essentially put in the same information as you did before in the part A, but you're changing the standard deviation from 2.5 to 0.79 because, again, we now have a sample size of 10. Again, that gives us this really, really tiny number, 0.005676. Again, this is that chart right there is all the information you would need to show. So answer the question. It is very unlikely, less than a 1% chance, that we would choose an SRS of 10 young women whose average height exceeds 66.5 inches. It's like, why is there such a drastic change? Well, again, remember, um, instead of taking a sample of one person, we're now taking a sample of 10 people. And so that's going to, the bigger the sample size, the less variability. And so because there's less variability, the likeliness of us getting an average height of 66.5 inches is significantly lower. And that is all we have for today. My name is Richard Chow. Have a good night.